Ladies and gentlemen, my name is János Karsai from the Borja Institute, University of Szeged. You certainly know me from the introductory Mathematica trainings organized by the SciExpets. In this new videos series, I would like to present some simple modeling applications using the Wolfram Notebook Assistant and other modern tools of Wolfram Mathematica. Now we start with the parametric curves, which are practically tools of visualization of motions in 2 or 3 dimensional or higher dimensional spaces. Actually, this kind of modeling problem is part of the introductory training, and it includes a lot of nice technical tools in mathematical programming. Let's consider a very simple example. We deal with it during this short video. That's the logarithmic spiral. Actually, asking Wolfram alpha and receiving the answer, I receive some particular figures and the general formula in Cartesian coordinates and also in polar coordinates, and also some people, some researchers who dealt with it. Now ask the Wolfram Notebook Assistant, what is and how to visualize this logarithmical spiral. Based on the answer, we can define the functions describing the spiral, but let's consider the answer. The general formulas are also given, and the code of the visualization tool is given also with a special version of the spiral. So based on the answer, the spiral can be defined in a general way, both in the Cartesian way and the polar system. If the code is considered, the spiral is considered with a special parameter, and we obtain the graph of the spiral in a very easy way, and also using the polar plot we can have the same figure. Now consider some more questions. How to plot the coordinates dynamically? This is the code the Notebook Assistant gives us, and then running the code I can obtain a row of figures. The x and y coordinates are obtained next to each other. My original application contained the coordinates in the same coordinate system, but anyway they are pretty much the same. How to draw the parametric plot dynamically? That's my question to the Notebook Assistant. The answer is correct. The code is given. Notebook Assistant gives me the result including my former definitions. So my former developments are also used in the answer the Notebook Assistant gives me. Okay, so my solution is also changing the final time dynamically is very simple. That's the parametric plot using the manipulate. That's pretty nice, and special functionalities, special options are also used in the manipulate. In the introductory training we learn those, we learn how to use them. Finally, how to plot the parametric curve in the extended phase space. That's also important. In that case the time coordinate is also included, so that's now a 3-dimensional space, and then we can see how it works. Based on introductory examples, we can consider the general definition. The function we consider now is mapping from the real line to the n-dimensional space, where R is the parameter space and R to n is the image space. The interpretation is easy. Now such a function can be the path of the motion in the phase space, and the time in that case in the motions is the time denoted by t. Also velocity tangent vector of the curve, that's the derivative, and the acceleration vector can be also plotted there. We will consider them how to do that. Actually the image of the function in the phase space is called as a parametric curve. The graph in the extended phase space can be also plotted. In that case the time is prepending to the phase coordinates. How to investigate such a function, such a curve qualitatively? Continuity singularity and finite t as a vector can be considered or coordinate-wise. Monotonicity is tricky, juicy, because ordering in the set is needed. Simple possibilities are coordinate-wise or compose a scalar function, or that's the norm of or the energy. The differentiability is defined by coordinate-wise maximum, minimum, meaningful only coordinate-wise or composed, again the energy. Concavity inflection points are meaningless in this situation, but we can consider the curvature, torsion, or other properties handled in the differential geometry. Now, there are some problems with these curves. When we plot the parametric curve, the time doesn't appear in the parametric plot. How to show the time in the phase space? Hence, we cannot see also the dynamics of the curve. We cannot see the speed, how fast the motion is. We cannot see the acceleration of the motion along the path. How to show them? How to resolve those problems? That's easy. We can use coloring, drawing the speed and acceleration vectors, maybe dynamically. We can also use stroboscopic plot, and we can combine these tools. Let's do them. Let me ask the notebook assistant what to do. How can I color the plot with respect to the time? Can I use legend anyway? I obtained the result, but now in the result the legend is not correct. That's what I wrote to the notebook assistant. Okay, I obtained the modified version. It was perfect, but in the legend the coloring was not correct. It's changing. I want the complete color scale on the whole interval. I needed to modify the figure. That's why we need some programming also in Mathematica, and we should not trust only notebook assistant. So my solution is, with some enhancement, is the following. You can change the time, and then in the bar legend I can show where the time exactly is. Even better, using the vertical gauge object in Mathematica, I can use the same, and this is very, very impressive application for this very simple visualization problem. Now the next problem is how to use the parametric plot and the tangent vector, the velocity vector, dynamically. I asked the notebook assistant, can I plot dynamically the moving point and the speed and the acceleration vector? I received a good answer, but unfortunately it's not correct, because it used the derivative of the spiral. Spiral prime is used, but it doesn't work because the spiral function is a function of two variables. I wrote it to the notebook assistant, and then I obtained a corrected version with something, but unfortunately the vectors and the curves were not in the same figure. But at the end I obtained the following figure. Look at that. Using my former applications, the vectors are also plotted. Using some additional work, look at my application. So now that's final result. Here in this plot I didn't use the vertical gauge to show the graphical change of the time. How can I draw stroboscopic plot? That was my question to the notebook assistant. It's so nice. It's perfect. No problem with the solution I got, but I included my additional developments, so the vectors are plotted and the strobes, the stroboscopic intervals are also plotted here. So I really like this answer. Actually, it's much nicer than my original figure was, because here I just plotted the points without the vectors. Now again dealing with the stroboscopic plot, I would like to draw the vectors at each point. The answer given by the notebook assistant contains some errors. I explained them here. There are some simple technical syntactical errors, and then after the corrections I obtained this result. Only the vectors and the points in the stroboscopic plot are plotted here, and my original solution before knowing anything about the notebook assistant is here. Look at this, very easy and a very nice application. You can see the input code of this statement. If you need, I can send it to you. Finally, notebook assistant could also help, but I did it by myself some time ago. The curve in the extended phase space is plotted, and some projections are also plotted on the wall of the bounding box here, so you can see. It's also useful figure in modeling the trajectories of differential equations anyway. Now, let's make some observations. Notebook Assistant can improve its former solutions. Answers are not deterministic. We need to verify the results, that's obvious, and we still need to learn programming tools, but Notebook Assistant means a great help in our developments. Concerning our modeling example, the parametric curves or 2D developments can be easily transformed to 3D motions. The same tools can be used if the curve is given as a solution of ordinary differential equations or delay differential equations or so. Creating a stroboscopic plot, good basis to work with processes given in experimental data or as solutions of discrete systems. Now, how to extend our applications to the three-dimensional space? For example, we consider a three-dimensional lissajous curve. It's not a big deal. Parametric plot. The parametric plot 3D statement can do. The legend is given using the coloring. That's it. And then using the colored parametric plot and the tangent vector, the speed vector of the motion is given. Here now I use the vertical go dynamically showing the time. That's just a simple stroboscopic plot and the stroboscopic plot with the tangent vectors. I guess it's a very attractive figure. And finally, we can animate the motion of the moving point in the three-dimensional space. Look at that, how it works. The point is moving, the tangent vector is moving, and the tail of the motion is well visible, and the time is also shown in the vertical go. So, ladies and gentlemen, I guess that's enough for today. Thank you very much for watching me, and now you can see this three-dimensional figure. We would like to continue this video with other topics. Next, by our plan, we will study how to investigate functions given in experimental data. It will include, among others, how to visualize lists, how to collect data, how to work with lists. We consider the list operations, we deal with the rule-based programming, and we consider simple numerical methods like numerical differentiation and integration, and also we consider some simple methods of smoothing for noisy data. Thank you very much again.